And the next presentation will be given by John Garbett, and is on open software in astronomy. John, if you please.
Yeah, thank you very much. So, good afternoon, everybody. My name is John Garbett, and I just want to quickly introduce myself. I'm a principal engineer currently working at Stack HPC. I've been working since about December 2010 on and off on OpenStack, and about the last 18 months or so I've been with Stack HPC looking at particularly at high performance computing and OpenStack and how to get all those working together. And one of the major projects we've been working on at Stack HPC is the Square Kilometre Array and various things around that area. So today I'm going to start talking about that. So first place to start is what is the SKA? And here I've got two artist impressions. Hopefully it's vaguely visible. The left-hand time, nighttime, is quite nighttime, but that's fine. So to start with, it's a radio telescope. So looking at the sky, trying to take better pictures of the sky. It's currently in a sort of coming towards the end of the design phase, hoping to start construction in April 2020, I believe. And the first thing to note is there's two locations. There's one which is mostly to do with mid-frequency, so that's the left-hand side. This is called SKA1 mid. This is planned to be in South Africa and the surrounding area. There's about 200 of those dishes, I believe, planned, roughly speaking, and they all get joined together to form one radio telescope in South Africa. And there's a second instrument, SKA1 low, which is on your right-hand side, and that's here, the thing that looks like a field full of metal Christmas trees, as far as they're about my height-ish in a field, the sort of little discs of them. This is the aperture array of low frequency. So why the Square Kilometre Array? Really, it's about taking better pictures. These are some infographics from the Square Kilometre Array project. I should say I'm talking on behalf of Stack HPC. I don't actually work for the Square Kilometre Array project. I work as a subcontractor for Cambridge University on technologies related to it. This is where we're looking at things. So really, it's about taking better pictures of the sky. How do we define better in terms of these pictures? Well, I have no idea, so I asked the scientists on this. Their infographic says the resolution, the sensitivity, and the speed of the pictures that they can take. And effectively, the Square Kilometre Array, both in the mid-frequencies and the low frequencies, are making a huge step forward in this. Now, from the computing challenge of this, those of you that have been ignoring what I've been saying and reading the rest of the slide will notice that that bigger picture, better view of the sky, basically means a crazy ton amount of data going around the place. And these are data rates that are pretty damn scary, particularly when you start thinking about the idea of 24/7 operation, trying to get the most money out of these telescopes, always looking at bits of the sky. And this is a radio telescope, so it can kind of see, virtually from horizon to horizon. So you've got very long observations happening. So the main problem I want to talk about is how do we actually do some science with all of this data that's flowing around. So I'm going to talk about three things. The first thing I want to look about is the science data processor architecture. So this is the part of the Square Kilometre Array that's actually doing the number crunching. So each of these telescopes, the SKA1 mid and the SKA1 low, will both have their own dedicated supercomputer to process the data coming from the telescope. So the basic idea is the radio telescope is in an area of radio silence. So that would be a kind of awkward place to build a supercomputer. So then there's a very long cable that goes to the data center where all the computing happens. So you've got loads of, effectively, what's planned is lots of 100 gigabit Ethernet links with UDP coming into the data center, and then we need to do something with that inside the science data processor. So step one is the data is coming in to the switches, lots of UDP coming in. The overall approach here is to try and use a very large parallel file system, a buffer, to try and disconnect the ingest of the data with the processing of the data. The rates at which these need to happen need to be different, so the best way is to try and buffer between those two things. So the first part is really to ingest all this data and get it into a buffer so that we can then later take that data out of the buffer and reduce it down to the data product, which effectively means that you're doing Fourier transforms and averagings to get pictures of the sky. So you've got the UDP coming in, get to the disk, try to create the sky pictures. Once you've got the sky pictures, you're trying to deliver those to the scientists across the globe that process them and find interesting things in them. And that's the general plan. So let's zoom down a little bit further into the detail of the problem here. So what does this look like in each of the sites? So for each site, you've got the data, as I said, coming in from the telescope. Certainly for the SK low, there's a central signal processor, and effectively that takes the voltages and things from the telescopes. So the data rate coming in to the science data processor is about 1 terabyte a second, roughly speaking, which is a lot of UDP not to drop on the floor, to be fair. The next step is, as we said, to try and get that ingested. So if we take a little zoom further down, got the data coming in, we've got these sets of real-time processes to ingest the UDP. They're roughly writing into this tiered buffer system about 1 terabyte a second, and they're reading out for the batch processing order of magnitude between 4 to 10 terabytes a second. And for the output, the data products is an order of magnitude smaller. These are all estimates based on what we think the processing to be that will happen, but the processing, these science workflows are not yet decided. Things may change between now and when the telescope actually comes online. So just estimates about the data processing. So from the batch processing to the data products, it's expected to be about 10 gigabytes a second-ish, such that you can then push that all out to the regional data centers using a 100 gigabit link and try and keep all of this. And again, the challenge is to try and keep all of this running 24/7. Okay, so this is a massive eye chart of an architecture, and I'm not really trying to go through this apart from to say I've been talking really about the main visibilities that are flowing through the system, as the scientists would call them, the main data. But really the buffer is trying to be this general purpose storage component within the system. There's lots of different places that have to use this. So when you read out the long-term storage before you actually deliver the product to the regional center, you're trying to use the parts of the buffer for that as well. So just to say, the sizes of these buffers are going to be quite variable. So the buffer component, what it's actually trying to present to the system is this abstraction of a data island. So as you'd imagine, the data island is just trying to define, it has certain characteristics such as, do I need this data to be of the, able to read very fast? Do I need to have it to be a particular level of resiliency? Do I need to do replication on this, or do I just need it to be fast right now? So the idea is that different components define their needs as a data island, and then that can be scheduled to decide exactly which resources within the system you're going to consume. Okay, so let's go over just quickly like the key challenges here. The main one is the massive data rates. How do we get a parallel file system that can actually sustain these data rates? How can we estimate its cost so that we can start to do budgeting? The second thing is here we've got a lot of control plane activity beyond the data rates, there's a lot of different size buffers that are needed at different times and needs to be copying between the tiers of buffers if that's what the budget basically means. You can't just throw the most expensive storage hardware, network hardware at this problem. You need to be a much better efficient use of resources. So we need to have a tiered buffer, so we need to deal with that modeling. And going back to the keeping the budgets right, the idea here is to size the system for average load. What I mean by that is when you go back to the observations that are happening, depending on which bit of the sky you're looking at, your observations will be for different lengths of time, just because you physically can't see that bit of the sky for 24 hours because the Earth moves. Well, you know what I mean. So for different observations, there'll be a different size buffer, because the longer you're looking at it, the more data you're going to come in. We need to try and slice and dice the system in a way that works, but still keeping that sustained data rate. Okay, so the next two parts of this talk are going to talk about how do we actually go about prototyping the system and exploring the problems better. So the first part of this is what I call the Software Defined Supercomputer. What we've built is the system we've called Alaska, SKA, which is a performance prototype platform. This is two racks of hardware hosted by Cambridge University, and this is where a lot of the Stack HPC work has been focusing. This we've turned into a bare metal OpenStack cloud, and this has allowed us to slice and dice the system to actually explore some of these problems. And let me try and dive into how this has helped. So the hardware itself is trying to model a small fraction of what the final system could be. The core part of it is in the 25 gig Ethernet here, we're trying to mirror this idea of, this is trying to be the network that the UDP comes in. So the telescopes will be sending to the top of rack switches at 100 gigasecond, and then you get the UDP packets coming into the nodes. So right now this has been running, the simulators for the telescopes run on one rack, and that generates all the packets that go across to the other rack, where they try and simulate the ingest nodes. And there's ingest nodes trying to use high-speed networks such as InfiniBand to connect disparate storage systems to disparate compute systems to try and deal with some of this dynamism. So when I say software-defined supercomputer, what do I actually mean? What I'm trying to say is, how do we build up reusable pieces that people can share when building up their workflows? These workflows will evolve over time, and a lot of this work has been about working with the scientists to see how well the existing systems could be packaged up in this way, so we can basically allow the scientists to do their thing, while the network engineers and the compute engineers optimizing other bits and pieces can get on doing their thing and sort of grease the wheels of innovation. So in an OpenStack world, none of this is particularly new, but this is just applying it to the science world. So the idea of just trying to package up applications using containers and Ansible and just make these pieces that we can slot together. So one example I wanted to pick up on was some work we did with the Kubernetes cloud provider OpenStack. So I spoke about this abstraction of a data island, and we were trying to look at whether we can actually use the idea of the Kubernetes abstraction of volumes to map to this data island concept, and how all of this thing could glue together and what it actually means. So this is a big diagram with lots of boxes that have millions of moving parts inside. Let me try and describe what's going on here. If you would like to see a recorded live demo of this, I put a link, I think, I will put a link on the presentation to something I did at the OpenStack Summit in Berlin, where we demoed this working. But what we've got is we've got OpenStack Magnum that we're using to create the Kubernetes cluster. So Magnum can resize the cluster depending on the size that's required. So you state how many physical nodes you need, and that stamps out the Kubernetes cluster. It's actually using Ironic underneath, so you get the whole bare metal machine. There's no hypervisor in between. So that gives you a set of machines. You've got raw access to the compute. Use Kubernetes in the usual way to create the containers that you need and connect them between your machines. But these particular containers are backed by the cloud provider OpenStack's OpenStack Manila Ceph native plugin. Let me go through that a second. So what happens when you create the volume in Kubernetes is it talks to the cloud provider OpenStack code, which creates a share of the appropriate size within Manila. In this particular case, we're using Manila's CephFS backend. So actually what it was doing was creating share quotas and namespaces within CephFS, and then exposing them appropriately into Kubernetes. But what this has given us is a way in which the scientists today working on the workflows can actually start using this model and saying, this is the size of volume we need, this is where it needs to be connected. And because it's using Ceph as the backend, this is attached in multiple places in multiple writer, multiple reader mode. So it's exactly the kind of thing you need here. One particular aspect of this to look at is the name shares. So when you create your volume, you can say, I want to use this particular share in Manila. So you reference particular share in Manila. That share in Manila may have a particular frequency band of the information you need. If you need to attach to several different frequency bands, the idea is that you can create those set of abstractions that are saying, I need to connect to all these different frequency bands together on one machine. And this is one of the problems with the placement that we have to deal with in the system, is that while you can have an element of ensuring that you have the data local to your compute, at some point in these algorithms, you need to join up, in many of the algorithms at least, you need to actually join up all the different parts of the sky if you've gone in the visibility, if you've divided the sky up, or you need to go across all the frequency channels more likely. And so in those cases, you need to actually go between racks where you've, let me try and describe that better, 1 second. Yeah, so in some cases, you can't just put all the compute local to the storage. In some cases, for one particular observation, you kind of need to see across the whole, for one particular workflow, you need to see across the whole buffer in particular cases. So if you go back to this data island picture, most of these prototypes, well, most of this prototyping work has really been, can we join all these pieces together? Can we do the dynamic provisioning of, of slicing and dicing this piece up? Does this set of abstractions work for us? And working through those issues. The big risk we haven't addressed so far is how do we deal with these data rates? We deal with it while you have laptop locking up, it would seem. Awesome. One second. Well, it's happy now. Okay, so this third part, the second piece of work on prototyping I want to talk about is the Cambridge Data Accelerator project. And this is where we've been working on a project where, while it's not directly targeting the SKA, it's a resource for testing these very high data rate parallel file systems and how to explore some of this slicing and dicing. So the basis of this project has been using Cambridge University's cluster, which their supercomputer that they're currently calling the Cumulus UK Science Cloud. It's really got, there's kind of two key parts of it. It's the Cumulus part, which is a mix of Intel Xeon nodes and KNL nodes, and there's a second side which is the GPU side. For this particular project, we've been focusing more on just the OmniPath part of the network, which is on the Xeon and KNL. But the main thing is the storage offerings. So this is quite a traditional environment in the sense that they've got a global Lustre system that's servicing most of their users. They've got more and more users where they've got workloads that are I/O bound. You know, their Lustre file system works great for the general purpose needs, but for the users with big simulation runs where they've got loads of small files, the metadata servers are creaking, and for, you know, when they're really pushing lots of data through, you really want something that's more dedicated. So the Data Accelerator project is trying to, how can we address those users' needs better? So just to highlight the size of the system, if you look at the top 500 list of supercomputers, because of the two networks, it's kind of, the system's got two entries for the two different halves. Number 87 on the top 500 in November 2018 was the Cumulus side. It's about 1,200 machines right now. And the Wilks 2 GPU clusters on the other side, just to a side. So how did the Data Accelerator project go? Well, it's actually got two entries for the IO500. So we're using the IO500 benchmark to see how we could get, for the all of the hardware in the Data Accelerator, how fast could it go? Using Lustre, we're able to get number 3 on this IO500 list, and number 7 using BGFS. So we tried the two different file systems on the same hardware. It's not quite the same client count. It's pretty impressive from what we were able to do, and I'll go through that in more detail. I should say at this point that the IO500 doesn't currently have 500 entries, so it's a little bit unfair saying that number 3 is the third in the world. There's not that many more entries if you scroll down that list, but it's a good benchmark that's starting to gain traction. So what is the system? It's currently targeting about 0.5 petabyte. Currently that's spread across 24 machines. Each of the 24 machines have 2 Intel OmniPath adapters. And I'm going to go through sort of what interface do we give the end user with this system. From looking back at the original data rates, if you do a marketing trick of changing bytes to bits, it looks like it meets the requirements. It's the best bit of marketing I've done. But, you know, I'm an engineer, so I tell you about it. So yeah, it's close. The bit I was talking about, the data islands, it means it's certainly good enough to do one data island of what the SKA is wanting. And I want to sort of go through a few interesting stories about the benchmarking. I had some sort of conversations about this, and people said it's really interesting. Benchmarking is very tricksy. But just a few things. When we were looking at this benchmarking of the system, we were having very unpredictable results between the different runs. We were actually using the production cluster, so it's picking at random different compute nodes and running on them and trying to just do sort of, you know, how can we get one node maxed out? It turns out that this setup, the IOPS, even running Lustre and BGFS, basically the network turned out to be the bottleneck very quickly, even with the 2 OmniPath adapters on the box. So what we actually found was this OmniPath network is a fat tree network. So effectively, you've got lots of switches with lots of 100 gig links. So that if you look at the top of rack, one switch has it's a 2-to-1 oversubscription. So you've got sort of two cables going to the core, where you've got two cables going to your compute nodes and one cable going to the core switch, all of the cables in the switch. And this core switching area was effectively where we were seeing saturation, because the routing algorithms weren't adaptive enough for the network load. So you're actually able to saturate some of your network cables. So it's actually ended up testing some of the network routing much more than we were anticipating. There's a lot of stress on the network. Another thing we found was using these particular SSDs, the P4600, they remind me a lot of my son trying to walk towards me. And bear with me with this analogy. They're very optimistic to start with. You're like, wow, these are the most amazing things ever. They're way better than the spec sheet. And then they sort of trip over and fall and then get going again, then sort of crawl towards you and then keep going all the way around the house and run loops around you. So what we found is that it's effectively reading around the accounting on the, where your block is stored. You hit that you seem to hit the next, it's almost like the data structures have got, extra levels are appearing in the data structures, and it just gets that little bit slower. So you have to be very careful about sort of getting that steady state of the system to say that that's what the system's going to do in real production. And doing a secure erase of the disk gets you back to its sort of very happy, peppy, wanting to run about all over the place self, which is really interesting. Although at least it meant we could actually repeat experiments. We saw the repeatable results, but yeah, it was interesting. Okay, so how we're actually exposing this to users. For this particular Cumulus system right now, I'm taking a subset of the system. We're trying to get OpenStack on top of it so we can have stuff other than Slurm on this system. So we're trying to do the same bare metal / hypervisor trick from the P3 system. But right now, the majority of users are accessing the system via Slurm. Slurm has a concept of a burst buffer within it. It's already all in production in several sites. The only working driver for the Slurm burst buffer right now is the Cray data warp driver. And because of that, that's the one we decided to integrate with. What that actually does is it talks to a CLI tool. So Slurm just shells out to a CLI tool, telling the CLI tool, this is what the user has requested. Here you go. By the way, now I know this is the compute node. Please mount it on the compute node. And so you've actually got a contract with Slurm. What we've done here is done a little bit of integration work with some Go code, just to basically take those commands from Slurm and then update a data model, and then basically try and distribute that between the burst buffer nodes where it just shells out to Ansible to go and create the correct file systems. Let me talk about this is going to really annoy me if it keeps saying this. I'm going to talk about the data flow between all the different bits of this. Maybe it's just my keyboard that's gone. Anyway. So in terms of informing the control flow, for the SKA work, the hot tier, cold tier, sort of tiered buffer system has exactly these same properties that we're trying to fix and trying to sort out. You've clearly got a setup phase, you've got a teardown phase at the end where you release if you sort of read both ends together, it's sort of easier to understand the system. You've got the setup and teardown. You also got the data staging in and out. So users can basically say, please create me this burst buffer of this particular size. Please get this data ready for me within the burst buffer for when my job starts. So that means for a particular user, you're not wasting valuable CPU time copying data about. The data is already ready in the burst buffer for when the CPU nodes are chosen and then assigned to that particular job. So right now, if people tried to copy that themselves, you'd be charging them CPU time while they do that copy, which may be a significant amount of time. So this system actually uses the burst buffer nodes themselves to copy from the existing filing systems to the high-speed one. That gets it already there for the job. What the user actually gets in terms of their environment in Slurm is they get environment variables telling them where the burst buffer has appeared. So if you've requested to attach to several persistent burst buffers or one per job burst buffer, you get different environment variables telling you what's happening. So what does this actually look like from the user perspective? So if you think of the user requesting a per job burst buffer, and they're requesting it to have the global namespace and the private namespace, they might have their code running on this host 1 and host 2, and there'll be a set of environment variables that point to those top 2 locations. One is a share, one is basically a symlink to a shared space in the filing system, and each of the hosts have their own private spaces. And really, it's just to avoid contention. Another thing that actually this can be used for is to try and simulate high memory nodes. So one of the things we want to try, particularly for the SK work, is how well some of the codes that need to have the whole of the Sky model in memory at any one time, if we can actually use disaggregated storage in this way as swap, if that's actually fast enough for those needs. For some codes, it may well be. The testing is currently a bit inconclusive. Haven't really got the actual results on that yet. Try to see if we can use this for swap as well. Okay, so I just wanted to review where we've got to, how we try and, what things are we doing here. So the SK buffer is trying to fix these problems really. It's trying to have a flexible architecture, and the flexibility in this sense, what I mean is allowing for the different sizes and different jobs by slicing and dicing the buffer into different sizes, and having that the ability to say that this data and this compute is close, or this is the one case where we need to see data no matter where it happens to be. Try and express those requirements appropriately so that you can do the right optimizations. We looked at some of the control flow prototypes, the Kubernetes work where it ties into Manila, so you can try and use these abstractions to give the storage in the different parceling ups that it's needed, and try to look at the prototypes to get the data rate as close as we can to what the SK is needing. So how to get involved? A lot of this work we've been talking about in the Scientific OpenStack SIG. It's quite an interesting group of folks get together. A lot of the OpenStack summits, there'll be a group of different talks and interesting conversations about people focusing OpenStack usage on HPC and that kind of environment. Also, if you wanted to have an overview of how OpenStack can be used within these kind of areas, there is a sort of miniature book PDF that you can read through on what's going on. That's a great way of saying hello to people doing similar work. For that Go piece of code for integration, I was hoping to be able to give you the repo to the Open GitLab, the Git repository. Haven't quite got there yet to get that sorted. I'm hoping that'll be really soon, which is annoying, but close. But we've been having conversations about this project within the SIG, and that will certainly be one way of communicating out what's happening. So yeah, thank you very much for your time, and thank you to all the people supporting the project. This can be done without loads of help from folks across the SKA project, different people at Cambridge. Dell and Intel have certainly helped with a lot of the work on the data accelerator. But yeah, thank you all very much. And thank you. Now we've got time for questions, I hope. If people have got questions, I'm hopeful a microphone might be able to get to you. Any questions? Oh, sorry, there's a question here. Or maybe shout and I repeat your question. Yeah.
Okay, so you show this connection between Slurm and data warp from Cray, but then you show that the ACD was actually using Ansible to have hardware. Why you need that? I mean, you already have the Kubernetes, Slurm on top of Kubernetes, and then you already have the hardware there. So why you need Ansible to deliver the hardware? I didn't understand that.
So let's talk about your, let me paraphrase that. You're saying here, why use Ansible? So in this particular case, this is on the Slurm system. So there is no Kubernetes running here. No. So this, my hope is that this system, so basically you've got, the Ansible here is running on the storage nodes. So the data accelerator nodes is where you're running the Ansible. And that's effectively, you know, when you're doing the provisioning, it does the provisioning of the Ansible across the machines and the teardown in the same way. My hope was that I would use pre-existing Ansible to do that. In the end, it's actually home cooked. But the idea is it's just an easier way of extending this system, is rather than trying to re-implement what Ansible does, we just shell out to Ansible to do the appropriate thing for the appropriate file system. So BGFS versus Lustre, it's the same inventory, same set of variables, and you just sort of, you flip the playbook, basically. Cool. Well, thank you very much. I'll be down here if people want to have a chat, but that's great. Thank you.